Welcome to the Potato Podcast. We keep it chill, raw, and a little fried. Just like a good potato. Sometimes deep, sometimes totally random. No filters, no fake vibes. Just real talk, weird thoughts, and good energy. Let's get into it.
Okay, let's jump into the deep dive. This is where you bring us the sources, and we really dig in.
We take that material, you've gathered articles, notes, whatever it is, and pull out the core ideas.
Exactly. We try to help you get truly informed without, drowning in all the details.
Think of us as guides, really, just distilling what's most important, based only on the material provided.
Right. And for this deep dive, we're tackling something absolutely foundational, but maybe a bit hidden: computer engineering.
Mm-hmm. And based on the source you gave us, looks like a pretty comprehensive article exploring the field. Our goal is to unpack it.
What is it? Why is it this, unseen layer beneath everything digital?
And why is understanding it actually quite crucial today? That's what the material seems to be getting at.
Yeah, the sources point to this really interesting mix: hardware and software, the physical stuff and the code.
It's where logic gates meet programming, and the article suggests the impact is very tangible, real world.
So let's unpack this. It's so easy these days to just focus on software, isn't it? Apps, websites, AI. That's what we see.
That's the interface layer, absolutely.
But the sources you provided immediately make us look deeper, right? At computer engineering as the essential foundation.
That's a key point the article makes straight away. It defines computer engineering as a hybrid. It sits right at the intersection, sort of between electrical engineering.
The circuits, the electrons.
Right. And computer science algorithms, software structure. The computer engineer designs and optimizes that whole ecosystem.
The hardware and the software working together.
Seamlessly, ideally. That's the goal.
So it's more than just writing a program. I liked how the source contrasted the questions they ask a software engineer might ask.
How do I write this program effectively? Something like that.
But the computer engineer?
Their question, according to the source, is more like, okay, given this program, how do I build the actual machine? The chips, memory, everything, so this program runs fast, uses less power, and is reliable.
Ah, okay. So optimizing the engine for the software?
Precisely. Making the hardware perform at its peak for the software demands.
And that dual nature seems key. The sources really hammer this home. They aren't just hardware folks or software folks.
No, they have to be fluent, really, in both domains.
Yeah.
Comfortable thinking about, say, processor architecture.
The physical layout.
And also the low-level software systems firmware.
Yeah.
Drivers that talk directly to that hardware. They're the bridge.
That makes sense. It's central to what they actually do.
Absolutely.
Yeah.
And, to really grasp why this field exists, the article suggests a quick look back. How did it even emerge?
Right. It wasn't always a distinct field. The source traces it back to the latter half of the 20th century.
Yeah, during that huge shift in computing, moving from those, room-sized mainframes
Wow, yeah.
towards devices driven by the microprocessor, everything started shrinking but getting way more complex internally.
And engineers realized something crucial then.
They realized that just writing clever software wasn't enough. For peak performance, for reliability, you had to understand how the instructions were physically being executed by the circuits.
You couldn't separate them anymore. The software's potential was tied directly to the hardware's capabilities.
Exactly. And that created a need for a new kind of engineer. Someone who could design the core hardware, CPUs, memory, I/O.
Physical components.
But also write that really low-level code. Device drivers, firmware, the stuff that acts as the direct interface.
The translator between the abstract software commands and the physical actions of the hardware.
And that core need, that duality of skill, hardware design, and low-level software control, the article says that's still the heart of computer engineering today.
Okay, so if they're bridging this hardware-software divide, what are the specific areas they actually work in? The source breaks it down.
It does. It lists core areas like digital logic design.
Building functions from basic on-off switches?
Essentially, yeah. Designing circuits at that fundamental level, then microprocessor architecture, embedded systems, which are computers inside other things.
Like in cars or medical devices.
Yeah. Exactly. Also computer networks, operating systems. And it mentions related, often newer branches too, like hardware-focused cybersecurity or building specialized chips to accelerate AI.
Even quantum computing hardware challenges. Wow.
Yeah, it's broad.
So what might an engineer do day to day in one of those areas? The source gave examples, right?
It did. It could
Mm.
be anything from, say, designing the layout of microscopic logic gates on a silicon wafer,
Dang.
to architecting memory hierarchies, figuring out the fastest way for a processor to get data. Or maybe working with FPGAs, which are like programmable chips, to create custom circuits.
Okay.
And of course, writing the firmware. That specialized software controlling everything from, I don't know, a smart appliance to an industrial robot arm.
It really sounds like working at the absolute bedrock of technology. What's the main goal driving all this detailed work?
Optimization, really. At the end of the day, it's about making things faster, smaller, more power efficient, more reliable, more secure.
And getting all the parts to talk to each other correctly.
That's a huge piece of it, yeah. The article mentions ensuring hardware components communicate effectively using, like, system languages, buses, protocols.
I2C, SPI, things like that.
Those are good examples for short distances.
Yeah.
And integrating wireless tech, too, like Bluetooth or Wi-Fi, right down at the hardware level.
So they're making sure all the different parts of the system can actually have a coherent conversation.
That's a good way to put it.
Yeah.
The source had a nice analogy there, the glue between the physical world of electrons and the abstract world of code.
I like that. Building the bridge and managing the traffic.
Exactly.
And when you think about where this work actually shows up, that's where it gets really tangible, isn't it? The source highlighted some amazing application diversity.
It's quite incredible, yeah. Take the automotive world. Computer engineers are designing the literal brains for self-driving systems.
Managing sensor data, like LiDAR.
Right. Processing huge amounts of data, running AI models on specialized chips for real-time decisions. It's intense.
And healthcare, too. Embedded systems and pacemakers, advanced prosthetics, imaging machines.
Definitely. Aerospace is another big one, needing ultra-reliable, fault-tolerant systems for satellites, space probes. Can't exactly send a repair person easily.
True. And even things we use for fun, like gaming.
Oh yeah, designing GPU architectures for realistic graphics, optimizing how game engines render visuals, high-speed memory interfaces. That's all computer engineering territory.
And just everyday consumer electronics, smartphones, wearables.
Constantly pushing boundaries there, making things smaller, more powerful, sipping less battery. Think about the sensors in your smartwatch tracking your heart rate that's embedded computer engineering.
So the takeaway from the source is clear. Anywhere computing interacts with the physical world, sensing, controlling, moving things, computer engineers are the ones making it happen.
They enable that crucial interaction. Okay, so how does someone actually become one of these engineers? Given that unique skill mix, what's the path? The source outlines it.
Yeah, the typical route is a university degree, usually specifically in computer engineering or sometimes electrical engineering, with a strong focus on digital systems and computing.
And the coursework sounds pretty demanding. Foundational stuff in digital systems, computer architecture.
Software engineering concepts relevant to hardware, plus a lot of math, obviously.
Right, and the specific technical skills they need are quite distinct. The article calls out things like C and C++ programming.
Low-level languages.
Yeah, close to the hardware. Deep knowledge of operating systems, especially Linux often. And using hardware description languages, HDLs.
Verilog, VHDL, those sound specialized.
They are. They're used to actually describe digital circuits for design and simulation. Plus, familiarity with microcontrollers, ARM Cortex is a big one, and hands-on experience with development boards like Arduino or Raspberry Pi.
So those are the tools and languages. But the source also made a strong point about soft skills being just as vital.
Absolutely critical.
Yeah.
Problem solving is huge, obviously. Rigorous logical thinking and an almost obsessive attention to detail.
Because one tiny hardware mistake can be a disaster.
It can be very costly and hard to fix, much more so than a software bug often. And collaboration skills are paramount.
Why collaboration specifically?
Because they often work right at the interface between different teams. Pure electrical engineers, high-level software developers, product designers, they need to speak all those languages and translate.
So they're the technical diplomats as well.
In a way, yes, holding it all together. And speaking of tools, the source went into the specific, pretty sophisticated tools and environments they use. It's definitely not just coding in a text editor.
No, far from it. For the hardware side, it mentioned EDA tools, electronic design automation, from companies like Cadence, Synopsys.
Right, incredibly powerful software suites for designing complex chips, laying out transistors, routing connections.
And simulation tools are key too, it said, like Model Sim.
Crucial. You need to simulate and test your digital logic extensively before you commit to actually manufacturing silicon, which is expensive.
Makes sense. And on the software side for embedded systems.
they're writing that firmware, often in C or even assembly. And they use specialized hardware debuggers, JTAG was mentioned, that let you literally pause the processor and inspect its internal state.
Whoa, like looking under the hood while the engine is running?
Kind of, yeah. It's vital for finding those tricky bugs where hardware and software interaction goes wrong. They also work a lot with real-time operating systems, RTOSs, like FreeTS or Zephyr,
Why real time?
because timing is absolutely critical. Think anti-lock brakes in a car or controlling a precision robot. The system must respond within a guaranteed time frame. RTOSs are built for that.
Okay. And the article mentioned even more advanced stuff. RTL modeling, ASICs, solvents.
Yeah, RTL is register transfer level modeling, a way to describe circuits. ASICs are application-specific integrated circuits. Chips custom built for one single purpose, very efficient. And SOGANs are systems on chip, basically putting a whole computer system onto one piece of silicon, like in your smartphone.
The sheer range of tools and techniques sounds immense.
It is. And the field moves so fast, new chips, new protocols, new architectures all the time. The source emphasizes constant learning is just part of the job. You have to keep up.
So with all of these skills and tools, what kind of careers are open to computer engineers, and what are the payoffs? The source gave a pretty good picture.
Yeah, a wide range of roles. You could be an embedded systems engineer, maybe working on medical devices or consumer electronics, a hardware engineer designing processors at Intel or AMD,
Firmware developer for networking gear, robotics engineer.
FPGA specialist creating custom accelerators, IoT developer connecting things to the internet, systems architect overseeing big projects, even hardware-focused cybersecurity roles or designing chips for machine learning.
And these jobs are everywhere, right? Big tech companies we all know, Apple, Google, Tesla, NVIDIA.
Definitely. Plus chip designers like ARM, semiconductor giants, defense contractors, and countless startups doing innovative things with custom hardware or edge computing.
And the source mentioned compensation is generally strong.
Typically very competitive, yeah. Especially in high-demand niches like semiconductor design, AI hardware, or cybersecurity hardware.
But beyond salary, the source circled back to that idea of tangible impact.
It did. And I think that's a key motivator for many in the field. You're building physical things that interact with the world.
Not just code on a screen.
Right. You're designing the systems that control cars, or analyze medical scans, or power communication networks, or enable robots to function. Seeing your design actually work in the physical world.
Booting up that custom circuit board you designed.
Or knowing your firmware is reliably controlling something critical, the source suggests that provides a really deep sense of satisfaction.
It sounds rewarding, but also incredibly challenging. The source was pretty upfront about the difficulties, too.
Oh, for sure. It's a deeply technical field. The article mentions working at really low levels of abstraction where tiny details matter immensely.
Like timing issues, hardware bugs.
Exactly. Dealing with nanosecond timing precision, chasing down hardware bugs that might only appear under specific conditions and are way harder to debug than software generally. Managing power consumption strictly, meeting tight-sized constraints, it's demanding.
Debugging hardware sounds completely different. Like you said, no easy fix sometimes.
And prototyping hardware is slower and more expensive than just recompiling code. Plus, the sheer breadth of knowledge needed is huge from semiconductor physics.
All the way up through software stacks and networking.
It's a lot.
Yeah.
But the source frames these challenges almost as part of the appeal for the right kind of person.
The satisfaction comes from overcoming them.
Precisely. Successfully wrestling with that complexity, solving those hard physical constraints, and making a real system work reliably. That's the reward. Making the theoretical actually function in the messy real world.
Making it real and making it robust.
Exactly.
So let's wrap up this deep dive by looking forward. Where is computer engineering heading? The source points to some really exciting trends.
It does. Things like edge computing are exploding, doing more processing right on the device, not just in the cloud. The Internet of Things continues to grow massively,
Billions of connected devices.
each needing efficient, reliable, embedded engineering. And then there are entirely new hardware paradigms emerging, neuromorphic chips that mimic the brain,
Wow.
and the fundamental work on building practical quantum computers. That's deep computer engineering territory.
And all of this requires engineers who can bridge the gap between these new ideas and functional hardware and software.
Absolutely. AI and machine learning are huge drivers too. Their computational demands are pushing current hardware to its limits.
Driving that need for hardware-software co-design.
Exactly. And specialized accelerators chips designed just for AI tasks. Computer engineers are central to creating those.
The sources also mention sustainability becoming more important.
A really key point, designing ultra-energy efficient systems right from the silicon level up. Reducing the massive energy footprint of computing is a major challenge computer engineers are tackling.
And privacy and security benefits from local processing.
Yeah, keeping sensitive computations on the device itself, enabled by powerful but efficient hardware. That's a trend driven by privacy concerns as much as latency needs.
So it's not just about building the tech, but shaping how it impacts us, its efficiency, its privacy, its environmental cost.
They're really fundamental in designing those aspects right into the hardware foundations.
Yeah.
They are indispensable for what's next.
Okay, so summing up this deep dive, based on the sources, the big picture is that computer engineering isn't just mixing hardware and software. It's really this dynamic engine of interdisciplinary innovation.
Where abstract logic meets physical electrons. Where circuits become smart devices.
And where mastering those low-level details enables all the high-level digital experiences we now take for granted.
The source paints them as the essential, maybe often unseen, pioneers building the literal physical foundations of our digital world.
So whether you're fascinated by what's inside your phone, or you dream of building robots, or you just love the challenge of making systems faster, smaller, more efficient, more reliable.
The sources make it clear. Computer engineering is one of the most challenging, impactful, and intellectually rewarding fields out there, especially if you want to build things that touch the real world.
And that final thought from the source really sticks with you, doesn't it?
It does. The future will not only be written in code, it will be engineered.
Makes you look at every piece of technology around you a bit differently, understanding the engineering that had to happen first. Something for you to think about with the devices you use every day.